Okay, first of all, I'm kindly ask you to summon if you can hear me well and if you can see my screen.
Yes.
Okay, thank you very much. Okay, so thanks to be here for those who are here and for coming to listen to what I'm going to tell you about the Beyond EPICA project. So first of all, my name is Barbara Stenni. I'm a geoscientist. I'm from the University of Venice, Foscari. And my background is I'm a paleoclimatology, and in particular, I'm studying the application of the stable isotope geochemistry to the study of the climate of the past from Antarctica ice core. I'm directly involved in the Beyond EPICA project, and the Beyond the EPICA project is part of the European Polar Cluster, and this is the reason why we are here. And what I'm going to do today is try to convince you that how much important is retrieving an ice core from Antarctica as much as all 1.5 million years. Here is a slide showing the outline of my talk. So during this talk, I will briefly introduce the paleoclimatology and the ice core. And I will go through the IPICS challenge of all the styles and why we are interested in retrieving an ice core old 1.5 million years. But before presenting the Beyond EPICA project, I will go through the EPICA project, which is the previous project of deep ice coring in Antarctica. And I will go through the main outcome of this project, but also I will show you some few new results. Then I will explain the Beyond EPICA project, the aims, the challenges, and where we are in the field. And I will close with some pictures and videos from the field. Okay, so first of all, paleoclimatology. So the climate scientists have an obligation to provide a realistic assessment on how climate will change in the future. So for doing so, we need to know the climate system, and the paleoclimatology gives us the opportunity to study the climate of the past using natural archives. And in natural archives, you have here some of them: the speleothem, the tree rings, the sediment, marine records, and the ice core. That is the topic of our talk today. On the right, you see that we are using in this natural archives, we are using climate proxy. The climate proxy are the indicators of past climate contained in natural archives. Here there are some examples, for example, the benthic foraminifera, as well as the diatoms, but there are many of them. So here we will talk about the ice sheets, the polar ice sheets in particular, and we retrieve how we obtain this information from the polar from this polar ice sheet is making ice cores. This is a schematic of an ice sheet section, and it's here is I would say an ice core going from the surface to the bottom. You see that if you choose a site which is in the inner side of Antarctica along the main dome, along the dome, you as you go through and deep the ice, you will go deeper in the past. Obviously, as we go deeper in the ice in the ice sheet, we have all the information as stretched, and so we need to, first of all, we will need to have a chronology for this. I also wanted to show you on the right the most important information that contain an ice core is both from a matrix and both from the gas phase. Here you have what happened in the upper part of an ice sheet, and so about at the upper part of the 100 meter, where the snow transformed into firn and then into ice. This is called metamorphism of the ice of the snow. So the snow here you have open pore. The atmosphere is free to circulate, and then after, when you reach the close-off depth, which is about at 100 meter in the polar ice sheets, you close the porosity, and so the gas go inside these teeny bubbles. So in this way, we can extract the gas from the ice core to obtain information from the past composition of the atmosphere of the past. Okay, from the Antarctic ice core, you have some nice photo here of an Antarctic ice core. Here is in the center, you have a thin section of a piece of ice with these white points. These are the bubbles inside, the air bubbles inside the ice. So for the Antarctic ice core, you can retrieve the past climate information, and this past climate information can go from the last decades, but up to the last hundreds millennia. So we can go back in time up to 800 kilo years before present. This is the EPICA project, but we can also focus on the more recent times. And what we measure on the ice core, we can measure different, we can have different measurements, and so different proxy. And some of them are, for example, the water stable isotopes that give you information on the past atmospheric temperature, or the aerosol concentration, or the content in the air bubbles of methane, carbon dioxide, the dust content, and so on. So this is not an exhaustive list, but it is just an example. Okay, so who is this guy? This guy is Willy Dansgaard, a Danish scientist. And this year it is the 100 here. It is the centenary of his birth. Willy Dansgaard was the one who understood that from the oxygen and hydrogen isotopic composition of the ice, we can reconstruct the climate of the past. So on the right hand of this slide, you have the oxygen isotopic composition of the precipitation and the temperature. And you can see that there is a good relationship between the two, a positive relationship. This is what we call the isotopic paleothermometer. Okay, so since I just want to briefly introduce you what is an isotope. So we have not all the water isotopic molecule, not all the isotopic molecule, the molecule of water are the same. So we have different mixture of isotopes inside this molecule. And the difference between these isotopic molecules is the fact that the lighter one has a higher vapor pressure, and so they will have a tendency to pass into the vapor phase. On the left hand, we have a short cartoon that will show you how it works, these water isotopes in the precipitation. So now it starts. So as the water evaporates, the water vapor evaporates, it will go through some fractionation processes. And after the formation of the water vapor, most of the light molecule will pass mostly in the vapor phase. And once you lose in the precipitation the heavier isotopes, which have a tendency to pass in the condensate phase, your precipitation will become more lighter. And when we arrive in Antarctica, it will be the lightest one. And all this process is controlled by the temperature. So from the measurements of the isotopic composition of the precipitation of the past, which are enclosed in the ice core, we can derive the temperature of the past. What is important here is it is not only the temperature of condensation, the final condensation temperature in Antarctica, so the final point, but also the starting point. So it is the temperature gradient between the source and the site. So The ice core research is highly collaborative at international level, and IPICS, which is the International Partnership in Ice Core Sciences, is a planning group which is currently composed of 24 nations. It is composed from ice core scientists, engineers, and drillers. And IPICS has 6 priority projects, among which the first one that you see here is the oldest ice. So to find an ice core, a ice which has at least 1.5 million years old. So here you have a figure. We will go through together to this figure. So at the bottom, you have the benthic stacked record of the foraminifera, which is a combined proxy of ice volume at deep sea temperatures. So here is the past, 1.5 million years, and here is the present on the right. This is a stacked record that shows us with this fluctuation between glacial period, interglacial period, glacial period, interglacial period, which has a component which is changing in the past. So not only the amplitude is increasing toward the present, but also the frequency, the cyclicity of this change is increasing. In the middle of the graph, you have the temperature of the past reconstructed from the water-stable isotope, what I just showed you before. And we see that with the temperature of the past, we stopped at 800 kilodegrees before present. And on the top, we have the CO2 record, which the blue is covering, is what is covered by the EPICA project from the previous drillings. And in the first part of the graph, we have some points, but we don't have a continuous records. And this information that we have from the carbon dioxide are coming from the boron isotopes, for example, in the marine records, or from the CO2 data from the blue ice area in Antarctica. We have also a shading in a yellow shading, which is the 40 kilo-year world. It means that here the interglacial cycle fluctuates on a cyclicity of 40 kilo-years, and then a 100 kilo-year world. In the middle, this reddish, it is what we call the middle Pleistocene transition. So the transition from this 40 kilo-year world to a 100 kilo-year world. But what caused this transition from a 40 kilo-year world to a 100 kilo-year world? There are some hypotheses, and all hypotheses are mainly centered on the idea that it became harder to deglaciate after the middle Pleistocene transition. So two hypotheses relies on the reduction in the CO2 concentration of the atmosphere in such a way that less energy is available for deglaciation during insolation maxima. The second hypothesis depends on slow changes in the bedrock material underlying the northern ice sheets from sedimentary regolith to crystalline rock. And so this change how the ice sheet can flow and determines a area of instability and thickness, and so the ice sheet becomes more vulnerable to orbital energy inputs. When I'm talking about ice sheet, in this moment, I'm talking about the northern hemisphere ice sheet that grew over the northern hemisphere during glacial times. So unless we understand what this transition, why this transition occurred, we really don't understand the current climate. So we needed to understand why this transition happens. And for having a knowledge of this, we need a continuous ice core records in order to have a continuous record of carbon dioxide stratigraphically ordered in time and covered in the last 1.5 million years. So here is just a timeline starting from the EPICA project, which was starting before this date in 1995 and ended in 2008. Then we go through the first Beyond EPICA project, the oldest, the site survey. It was a first part of the project, and then to the second part of the project, which started in 2019, which is a research and innovation action. So the first one was a coordination and support action, and now in 2019 started the research innovation action, with the drilling phase. So before going to the Beyond EPICA project, we just talk about the major outcome of the EPICA project. And first of all, but just to remind you, which are the oldest deep ice core in Antarctica. There are two oldest, quite old ice core. The oldest one, obviously, is EPICA Dome C. EPICA is the acronym for European Project for Ice Coring in Antarctica, and retrieved an ice core from Dome C. At the moment at Dome C, we have also the Concordia station, the French-Italian Concordia station. And then we have also the Dome Fuji ice core, which covered the past 720 kilo years before present, which is a Japanese project. So these are the two oldest ice core that we have at the moment in Antarctica. So here are the project, the results that we obtained from the EPICA projects and the drilling that was performed at Dome C. And in black, you see the isotopic composition, the delta D. It means the hydrogen isotopic composition of the ice, which is the proxy of the local site temperature. In this case, the present is on the left and the past is on the right. So this core, the black curves, cover the past 800,000 years. And at the bottom, we still have the benthic record, which is a proxy of the ice volume. And it shows a very good comparison between the two. And it also shows that the EPICA Dome C ice core cover the period from the marine isotopic stage 1, which is the Holocene, which is our current interglacial in which we are living, up to the marine isotopic stage 19.3, which is the last interglacial, which is recorded in the EPICA Dome C ice core. So, but perhaps one of the most iconic results obtained from the EPICA ice core was the record of the greenhouse gases, which show a strong coupling with the temperature. So at the top, we have the temperature as estimated from the water isotope. And on the middle, you have the CO2 content, the record showing the natural variability, so the glacial, interglacial variability of the carbon dioxide. And this variability stay between values between 180 ppm to 280 ppm. At the bottom, you have the methane. Also here, we have the present on the left and the past on the right. And these are 800,000 years. But what is clearly show us these values is the present day values of carbon dioxide and methane. You see these arrows on the left, which show our present day values of methane and carbon dioxide. So we don't have similar values over the last 800,000 years. Okay, now just a few words on a recent paper that we obtained from the EPICA I-score from the deuterium excess. What is deuterium excess? It's calculated from the. So I need to measure both delta D and delta 18O, and then I calculate this value, which is an integrated tracer of the hydrological cycle. So it is a proxy of the climate condition in the regions of moisture evaporation. So where the moisture where the vapor forms in the ocean in the low mid latitude of the Indian Ocean presently, and then this vapor will go through Antarctica and will precipitate, and so we are able to trace how this integrated tracer of the hydrological cycle changes with time. Here are reported the last 800 kilo years before present, the record that we obtained from EPICA Dome C. We called EDC, EPICA Dome C, which is in red. And we have the Dome F in blue and the Vostok, which is another deep ice core from the Russian team that covered the last 400,000 years. You see that we also the precession, so the cyclicity of 23 kilo years of the installation, and also we have the obliquity. And so the deuterium excess is in red. We see that the values are different because are different sites, but their variability is similar. However, we demonstrated that with the EPICA Dome C deuterium excess records, we were able to reconstruct that the variability of the temperature in the moisture source regions, and we see here in orange the variability of the temperature at the moisture sources. The deuterium excess is in red, and here is the obliquity. So also in previous paper, it was demonstrated that there is a correlation between the deuterium excess and obliquity. And we show here that indeed this anticorrelation exists between obliquity and the deuterium excess, but this is changing in time. So when we have that the deuterium excess and obliquity, which is a cyclicity of 41 kilo years, we have the deuterium excess and obliquity are anticorrelated during minima of obliquity, and this happens at glacial inception. And we see here when you have an orange rectangle, it means that we have an anticorrelation between obliquity and deuterium excess, and at the top you have the correlation coefficients, and then we have a positive correlation during the obliquity minima, which occur at the glacial maxima. So this variability of the temperature at the source and of the temperature at the site, which is in blue, has been obtained from the analysis of the deuterium excess. So these are just to show you some snapshots on the glacial termination, which are passing when we pass from the glacial to an interglacial. On the top in blue, so we have 9 termination in the EPICA I-score. And over this 9 termination, we have the temperature of the site as reconstructed by the delta 18O or the delta D values, and the deuterium excess, and so the temperature of the source. And what we observed that when we have terminations and interglacial, which start with the higher value in temperature, the deuterium excess is still high at the glacial inceptions, while in the interglacial, in the previous interglacial, which are characterized by not a maximum at the beginning of the interglacial, but just at the termination, we showed that there is a difference in the coupling between the moisture sources and the temperature in Antarctica. So these are just few results. I cannot go through much details on this, but if you want to ask me at the end. But now, so starting from 2019, the Beyond EPICA project, the Beyond EPICA oldest ice core, 1.5 million years of greenhouse gases and climate feedbacks, has been funded by the European Union, and it is a consortium of 12 partners, and the coordination is Professor Carlo Barbante. So what we promise from in this project, we promise to retrieve a continuous ice core record to bedrock, which cover the climate history of the mid-Pleistocene transition. So we need to have this record, and we need to derive the carbon dioxide and the temperature coupling and the sensitivity of carbon dioxide, and to during all the past 1.5 million years. Obviously, our first order is to obtain a high resolution climate record over the time interval older than 700 kiloyears, because for the first part, we have already the results from EPICA. So, okay, so, but where we can find these such old stratified ice, because we want to have a stratigraphically ordered ice, and so where we find such old stratified ice, we can find it in the inner part of Antarctica along the ice divide. Near the domes are these red colors show us, but there are also the blue ice area that can give us information on very old ice. Indeed, there are several nations who are working under the umbrella of IPICS that want to recover this old ice, not only Beyond EPICA, which is located near Concordia, but there are also the Australian, for example, at some kilometers from our new site. There are the Russian looking at Ridge B, there are the Chinese looking at Dome A, and the Japanese looking at Dome F. But there are also other nations. We are looking at the blue ice area, because also in the blue ice areas, we can recover very old ice, and so information also on CO2. The only problem with the blue ice area that we can have problems in ice flow, and so it's not easy to have high resolution records, and also probably stratigraphically ordered records. So these are the main projects, and Beyond EPICA oldest ice find the best suited position near Dome C, near the previous records. This map just show you quite nicely where the different nations are studying. So United States are studying both in area between South Pole and the blue ice areas of Allan Hills, the Russia Dome B, and the Chinese Dome A, and our European effort at Lide Dome C, and the Australian are quite near to us. Okay, so but how we find it, where to place this deep drilling? We find it this drilling after during the previous years of the Beyond EPICA. During the first year, there was extensive studies of geophysics of radar survey. So during the coordination support action, we have an extensive geophysical survey, and to find the best position for drilling this old ice core. So on the top left, you see this rectangle. So this is an enlarged view. And here it is a very nice figure at the bottom of the basal topography. And the white arrows show you where we decided to have this drilling. And here on the right, a nice photo showing the ice core site is here. So we are at about 40 kilometers from Dome C, from the previous drilling, and from the French-Italian Concordia station. This slide shows you the radiogram that comes from this extensive geophysical survey. And on the left, you have the position of EPICA Dome C, and on the right, the position of the new drilling Beyond EPICA. And so these lines are the isochrone that are dated up to about 600 kilo years before present, and so these isochrone are based on the dating that has been performed at EPICA Dome C. So this line follow the same age. You see here, there is I don't know if you are able to see, but there is a pink line, and below this depth, there are no clear. There is a lack in stratigraphy, and we think that we call this a basal unit, and this basal unit could be, but obviously we don't know at the moment. We could be a stagnant ice, and we will see when we will reach this. So from a preliminary timescale based on this radar survey and using a Dansgaard-Johnson ice flow model along with this radiogram, this isochron, we suggest, and this is the green line, okay? So we suggest that ice is very old atop this basal unit. You see, this is the basal unit, and then we have this stratigraphy. And so at the top of the basal unit, over the basal unit, we have, it is the model suggests that we have at least 1.5 million years at about 2,500 meters. So about above the basal unit. And here, what we suggest this model, this time scale, we have at least 14 kilo year every meter. And this is the resolution that we need if you want to have a clear resolving, if we want to resolve the 40 kilo year climate oscillations. So these data are suggesting that we can be confident in finding ice older than 700 kilo years in the last 200 meters in the bottom part above the basal unit. So several type of measurements are planned for the Beyond EPICA ice core, and several type of records will be obtained, starting from greenhouse gases, so CO2, methane, N2O, and obviously also their isotopes. From the water stable isotope, we can derive the Antarctic temperature, so the variability in temperature and precipitation, the ice sheet altitude, so proxy for sea ice for recovering the variability in sea ice in the 40 kilo year world, and many other proxy of, for example, for reconstructing the mean ocean temperature using noble gas thermometry or other measurements. So obviously, in order to meet the challenges which are required by the extreme thinning, we need to develop high precision, high resolution techniques. This one is, for example, is from Pascal Belleber, and it is a laser ablation inductivity coupled plasma mass spectrometry with the state-of-the-art on imaging techniques, which allow us to look in very much detail at the micrometer scale and to study the distribution of the impurities in the ice core in a two dimension. So it's incredible. And obviously, what other challenges which will be required for dating this very old ice will be the dating, the chronology. And just as an example, this is the krypton 81. It is a radioactive isotopes, and krypton is a noble gas which is present in the atmosphere. And krypton 81 is naturally produced in the upper atmosphere and has a long residence times, and due to its chemical stability is well mixed. So it can be used as a dating tool, but for dating ancient air trapped in polar ice, and is used in this range between 0.3 and 1.3 million years. It is an half-life of 230 kilo years. But up to a few years ago, it was required large amount of ice to make this dating. But now, thanks to recent development in the methods, the sample size has been reduced to less than 10 kilograms of ice for Antarctica. This is an example for we dated is from Ilaria Crotti and co-authors. We dated the deep part of the Taldice ice core, which is Taldice is Talos Dome is a dome near a near coastal dome of East Antarctica, where we have also an extreme thinning in the ice. You see this green rectangle. So also here the ice is very much thinned. And we use the krypton 81 to date this deep part. And it shows us that the Taldice record now covers also two more interglacials, the marine isotopic stage 7.5 and 9.3. And it was possible to use the krypton 81 for dating this very old ice. Okay, so here just focus on the fact that since the 2021, we have an ITN project which is focused on the training of a new generation of scientists, which we will need these young scientists for interpreting this new record that will be obtained from the Beyond EPICA. So Beyond EPICA and Deep Ice are tightly linked. And the project coordinators for the Deep Ice projects, these ITN projects, are Amel and Emily Capron. Okay. So now is a nice photo which shows the present day condition of the camp at Beyond EPICA Little Dome C. As I remember you that we are at about 40 kilometers from Concordia Station, and this photo is from January 2022, so it is the most updated one, and you show here the drilling tent, the sleeping tents. So it is an aerial view showing this remote camp, and with all the working and living containers for staying there up to from December to the end of January. And here I remember you that no field activities have been performed in 2020 to 2021 due to COVID restriction, but in the last field campaign, it was possible to finish this camp. So here are some images from the inner part of the drilling tent. You see on the left, this is the drilling system, and there is the trench. So we have a trench in the upper 5 meters, 5-6 meters. Here is the hole for the drilling system. And here are the ceiling of the drilling tent show with this opening, because and this is just a short lapse, if you see how it works. So in this way, the derrick or the drilling system can be lifted, and so the ice can be recovered. Okay. Okay, and now I have just a small, I hope it is possible to hear, I'm just starting a video taken from a dawn of the remote camp of Little Dome Sea.
A small town in the middle of the Antarctic plateau, purposely built for Beyond EPICA. This tiny village stands on top of the East Antarctic ice sheet, 3,230 meters above sea level, over 1,000 kilometers away from the coast, completely surrounded by snow. In summer, temperatures are around -35 degrees Celsius. And sometimes you have to deal with the strong wind. It's not easy to live here. Work conditions are hard. Everything is stored inside tents and containers, and everyday life is more complicated. The bedrooms and the bathrooms, the kitchen, the food storage, each activity has its own space, but the largest areas are dedicated to work, which occupies most of the time. Despite harsh conditions and some difficulties, the Little Dome Sea camp is now completed and will be the set for the Beyond EPICA project for the years to come.
So thank you for your attention. And here are some links to some interesting websites where you can have more information about this. Thank you. So, okay. If you have any question, please, you can open your microphone.
So I'm Angelo.
Ciao.
The drilling will start in the next year. So this year was
Yes.
just the preparation of the field.
Yes, this year was just the preparation. It was a lot of work. It was the camp was finished and the drilling system was installed. But now it was just the upper 130 meter of ice have been drilled. So the third. And the casing has been prepared, and now starting from the next field season, so the next December 2022, it will start the real drilling.
Yeah, and the storage is also ready for
yes. So yes, so the ice, okay, the ice that will be recovered will be part will be stored in part of the ice will be stored in Antarctica, and the part of the ice will come back to Europe in freezer at a very cold temperature at -50 degrees Celsius, and transported to Europe for the analysis. Obviously, for doing this, there will be some work to be done both at the Little Dome Sea camp, but also at Concordia station. There will be some processing of the core to be performed.
Thank you.
Other question? Okay, yes, just read from Bettina. Thank you very much for this very informative presentation. I have the link listed also on the website. Yes, yes. If you not could do then, yes, I can copy if you want all the link. Hopefully it works. I copied the link in the chat. These are the link for both the Beyond EPICA website, but also the deep ice. if I don't forget it. And but you can find it once you write down Beyond EPICA, you find you find the all the information about you find our website, and there are also the Twitter, Instagram, and Facebook links. Thank you. Is it okay, Bettina? Sorry.
Yes, thank you.
Okay. If there are no other questions, I thank you for. I hope. Sorry, there is a message, Marie. Barbara, I don't think that you see the link on the chat. Oh, sorry. If you want, open again the screen. I don't know why. Oh, okay, sorry. And copy again the link. Okay, here are. Yeah, there are. Marie is working?
Yes.
Oh, okay, thank you. Okay, so if there are no other questions, thank you very much for your attention. Hope to be, but if you wanted to send me some question offline, no problem. Okay. Thank you very much. Goodbye.